All right. Hey, everybody. Thanks for showing up to this late in the day session. Hopefully, I can keep things interesting so everyone stays awake post lunch. It's always hard to stay awake. There is some audience participation involved, so I'm going to expect to see everybody engaged. My name's Liz. Today, I'm going to talk a little bit about how you can make encryption a part of your security strategy. So I'm a developer. I joined a company that focuses on data privacy and encryption about a year ago. And frankly, I didn't know that much about it before I joined. And so a lot of this talk is really just sharing insights that I've learned and things that I've learned along the way as a developer that didn't know a whole lot about encryption. Do we have any cryptographers in the audience? Okay, well, I knew the Cloudflare person. I knew this was going to be the tough one right here in the front. I'm happy to hear this because it is going to be very high level. We're not diving into, primitives and like deep knowledge. So hopefully you will take something away from this, and if not, we'll just have some fun. So really, when I joined this company, I was thinking a lot about what does security actually mean? Because as I started going to like B-sides conferences and all of these different, security events, it means a lot of different things. There's a lot of different ways that you can approach security. There's a lot of different strategies that you can employ, right? I live in London. Has anybody been to London before? Yeah. Anybody been to the Tower of London? Yeah, okay. So if you go to the Tower of London, it's this huge, fortress. Well, huge for the time it was built, which was in the 11th century. And you basically just see all of these ways that they tried to enforce this fortress. Some which were quite sophisticated for the day, some we can kind of laugh at now. They have these big, giant concentric walls that are going around it. They have a moat, which actually failed the first time they tried to build it, which I found kind of funny. And then there are, kind of more sophisticated things that they built. They had these giant arrow towers, and you can see the little slit there where they'd actually have people waiting with bows and arrows to fire out arrows if they saw attackers coming on. So they didn't just rely on, the location of it or just the walls or just the moat. They had all of these different factors that they were using to try and keep everything inside protected, keep the people, the data that the people had, the crown jewels, all of these resources that are really important. So when we think about security, it's really not that dissimilar. We've got data. Sometimes it's customer sensitive data. Sometimes it's business secrets that you or your clients might be trying to protect. And when we're thinking about security, you want to employ many different strategies to ensure that hackers and attackers and different people can't get to it. One of the things we'll talk a lot about today as well is compliance. Compliance and regulation are extremely important, but it's also important to think of what you're actually trying to do, which is protect that data from attackers. There is a strategy that you can use that is actually even older than the Tower of London, and that's encryption. I'm guessing most of the people here today have heard about encryption. The earliest example that a lot of people cite of encryption being used was in ancient Greece, where the military would actually use a cipher or an algorithm to conceal messages that they would send to other members of the military. This is colloquially now known as the Caesar cipher, and it's pretty basic, but it worked in the day. What it would usually involve was taking whatever message that you had and then moving that letter over by a certain number of characters. And then that letter would become whatever letter it moved over. And we would assume that whoever was the intended recipient of the message would also have that key or that cipher. So once they got the scrambled, garbled message, they would be able to decode it. But if anyone intercepted it along the way, it would just look like a bunch of gibberish and they wouldn't actually know what it meant. So the example of the Caesar cipher here, you might have something like hello world. And then if you move that over by 4 characters, it becomes this unreadable message there. So obviously today we have much more sophisticated mathematical ways of doing this. Whether you're self-taught or you have a computer science degree or you did a boot camp program, I'm sure there's probably at some point you learned a little bit about encryption and how you might approach it. Like anything else with software development, things are constantly changing. People are constantly breaking these things, finding different ways to crack them. And as such, it's really important that as developers, we pay attention to what's going on, and we try to stay ahead of the curve and know what's coming down the pipe so that we can make sure that when we are building things, we're doing so with the highest level of security available. So if you look at this example from this Python library, you might already notice that there's a bunch of stuff in here that you're not supposed to use anymore. The other thing that's been happening a lot with software development, particularly in the last decade or so, is this idea of shifting left, which is moving security further up into the software development lifecycle. And this company, Sneak, I don't work for them, but I just thought this was a helpful diagram here of how we think about moving security further up. When I became a software engineer 7 years ago, pretty much the way it worked was like we build the thing and then we hand it off to the security team and they do the pen testing and whatever, and then there's remediations and we fix it. But as we all have probably experienced today, that's really not the way it works anymore. And oftentimes, if you are someone who might be called a DevSecOps professional, you're actually doing some of the security work yourself. And it's a lot. It's a lot to keep up with, right? On top of everything else that you have to do. There are some days where you look maybe like this person, where you're thinking, oh my gosh, how am I going to keep up with everything? How am I supposed to configure all of these different things? So again, today's going to be pretty high level, but hopefully you'll walk away having learned something new that might be helpful as you're thinking about how to approach security as a developer. So first thing that we're going to do is we're going to look at some different algorithms, both symmetric and asymmetric, and some of the schemes that are used. We'll talk a lot about key management because keys are basically the most important thing that you want to protect and be able to manage correctly in order for encryption to work, because if you don't protect the keys, there's really no point in even doing encryption. We'll take a quick look at a few common libraries and talk a little bit about ways to vet libraries or ways to look for libraries that you might want to use. There are some different places, both within your applications, that you can employ encryption, as well as doing it on the hardware side versus the software side, so we'll touch on that. And then think about what's next, both for you as a developer and also a couple of ideas like post-quantum cryptography that are on people's minds at the moment. So let's go into some basics of encryption. The first thing that I will mention that will come up a couple of times are these standards bodies. So these are sort of the groups that decide along with OWASP of what are the standards that we should use, what algorithms you should be using or you shouldn't be using. These are also the groups, if you have to comply with regulations or compliance, that will have those standards available. So you can always find there's like so much documentation, it'll make your eyes hurt. But these are the two groups that will get mentioned a couple of times. So in the basic example that we looked at before, really the process that happens here is you have a plain text message that's fully readable here on the left-hand side, and you want to send that to somebody. A lot of people use the example of Alice and Bob. So Alice has this readable plain text message that she wants to send to Bob. She only wants Bob to get the message, and anyone in between should not be able to actually see what it is. And the way that you actually conceal that message is by using a cipher, which is an algorithm that generates a key that can then be used to turn that plain text message into what's called ciphertext. So while the Caesar cipher looked pretty basic, the ones today look completely like irreadable. There's no way, you as a human person could crack it. You would need a computer and you'd need mathematical equations in order to do that. The cipher is really what handles that process, and we're going to take a look at some of the different ciphers that are used in order to turn the plain text into the ciphertext here. We have two different types of algorithms that can be used. There's symmetric and there's asymmetric. Symmetric means that you are going to use the same key to both encrypt and decrypt the ciphertext. This also means that the recipient needs to have the same key that the sender has. And there are a lot of benefits and a lot of challenges that come with using symmetric encryption. This is sort of a basic example, and it's like, simplest form of kind of what it looks like. The main thing that you can see is that it's using the same key in both encryption and decryption. There's just one, whereas with asymmetric, as we'll look at, there are two different keys. So some of the benefits is that it is faster because it requires less resources. There's less computational overhead. And because you're only using the one singular key, the key management process gets a lot simpler than it might for asymmetric. However, key distribution can be difficult. Making sure that that key gets to the other recipient requires a secure channel. And if you think about adding more people to the mix, trying to send them that key, it also becomes more difficult to scale. So kind of a general rule is that the longer the key size is, the stronger the encryption is. And I'm mentioning that now because this is the interactive part of the of the talk. Has everybody heard of Tinder? I see heads nodding. Okay, great, cool. Y'all know what Tinder is. So we're gonna play symmetric encryption algorithm Tinder. So I'm gonna put a encryption algorithm up on the screen. We're gonna take a look at its profile, see what we think about it. And then if we think that it's one that we should use, we'll swipe right. If we think it's not safe to use and it's not secure, then we'll swipe left. Cool, is everybody on board? Okay, yeah, you can go home and tell your partners that you were on Tinder today. Okay, so encryption algorithm Tinder. Crypto Tinder, you're on crypto Tinder. Crypto as in cryptography, not Web3. Okay, so the first one we've got here is triple des. So there was an original encryption algorithm created back in the 70s. So one of the very first ones that was sort of widely used by people called data encryption standard, I think. And so basically triple des just takes that same one, but it applies it in blocks of 3. So it's what's called a block algorithm. And it has key sizes of 112 or 168 bits and block sizes of 64 bits. What do we think about triple des? Swipe right or swipe left? Left, okay. Got some smarties in the audience. Indeed, we will swipe left. Yes, there have been vulnerabilities found in triple des. It's not supposed to be used anymore, and it should be, remediated when possible, and shouldn't be used to build new things. The next one that we have is RC4. So this is a stream cipher. So as compared to a block cipher, it actually encrypts everything byte by byte. So it's really good for large pieces of data. It will work a lot faster than a block cipher might. And the key size can be up to 2048 bits. Do we want to swipe left or right on the stream cipher? Left swipe? Good call. Yep. There have also been vulnerabilities found in RC4. So while there are some benefits to using it, it is not a secure choice. Next up, we've got AES. You have some different options for key sizes with AES, and each block size is going to be 128 bits. I feel like I probably don't need to say much more about AES. What do you all think? Swipe right or swipe left? Ooh, it depends. Okay, I like that. Can you tell me more? It depends on which cipher mode. Okay. So swipe right in some cipher mode situations, swipe left in others. Is that kind of what I like that answer. We will swipe right on this one, but sorry, what was your name again? as Ignan mentioned, it does matter which cipher mode that you choose. So you do need to be mindful of that. If you are choosing AES, AES might be the most widely used cipher at this point in time. And because there's all of the different configurations you can have with it, you just need to be mindful of which one you're choosing. The last one that we've got here under Symmetric is Twofish. So this is based on an open source and royalty-free algorithm called Blowfish. It has key sizes up to 256 bits and a block size of 128 bits. Swipe right or swipe left? Anybody? Now I'm nervous because you didn't say anything. It still depends on the mode. It still depends on the mode. So this is one that's approved to be used. So we'll swipe right on it for today. But again, yeah, it depends on the mode as well. So next we'll talk a little bit about asymmetric encryption. So this is also sometimes called public key encryption. This requires the use of both a public key and a private key. And so the private key can only be shared with users that are supposed to have authorized access, but the public key can be shared anywhere. You likely have probably seen people sharing their public keys on social media, in email signatures, anywhere. So that's the benefit here, is that you can share the public key anywhere, but again, the private key has to stay protected. You can see here that you do need both keys in order to encrypt or decrypt a message that's going through. You can't just have one or the other for it to work properly. The benefits here is that it is more secure. So as compared to Symmetric, because you have both of the keys, it's a better option. And you can share that public key everywhere. So distributing the key and doing the key exchange can be a bit of an easier process because it doesn't require a secure channel in order for that to happen. It is a slower process and it's a more expensive process. The keys are quite large. And so that's kind of where you might run into some challenges when you're using these type of encryption algorithms. Okay, so we're back on Tinder again. We're back on crypto Tinder. And let's just dive into it. So first we've got RSA. This is based on the idea that it's difficult to factorize a large integer. It can have key sizes of either 1024 or 2048 bits. Right or left? Left. Oh no, oops. Sorry, this was wrong. It was supposed to be left. So don't use this. The graphic is wrong on this one. You should not use RSA. this is the one that I think I meant to put it on there. Elliptic curve cryptography, it's based on the algebraic structure of elliptic curves, and it can be used with key sizes up to 256 bits. So right or left for elliptic curve? Right, yeah, there we go. So this one is one that you will want to use. I think that I've seen it more anywhere than I've seen any other encryption scheme. At the company where I work, this is what we use, along with the Diffie-Hellman key exchange, which we'll talk about a little bit later. So you might be thinking, what about MD5 or SHA-1? Because I thought that at one point as well, but these are hashing functions. They are not actually encryption. You can't reverse them and get the message back or get the plain text back, but you also don't want to use those either. So most of the time, you're going to be using a hybrid crypto system. You're not really using just one of these algorithms. You're using a combination of them, as well as something in tandem for actually doing the key exchange. So you might hear these called hybrid crypto systems or encryption schemes. There's some confusion or like debate over using the word protocol. I don't know. Do you have any, like, I've just seen people arguing about, like, is a protocol a scheme? Is a scheme a protocol? I feel like I've just seen the word scheme way more than I have the word protocol. So that's why I went with that. Yeah, I think that makes a lot of sense. So, so what he was saying is that a protocol is more like a subset of a scheme or a standardized practice like TLS. So, schemes can be something that you just decide that you want to put all together. It's not necessarily a standardized thing that many people are using and agreeing upon. So this is an example of what a hybrid scheme might look like for encryption. And there's a lot of protocols that are built this way so that you are actually using both symmetric and asymmetric. You're probably establishing the connection using asymmetric methods. And then once that connection is established between the two parties, any messages that you send back and forth to each other can be using a symmetric key or that one singular key rather than the public and the private. And then this is what it looks like if you are using it for decryption. So same process there of just establishing the connection and then using the symmetric key. These diagrams are also from this book called Practical Cryptography for Developers. I have found it really useful for just wrapping my head around cryptography and ways to practice it. So I definitely recommend it. It's available as a repo and also as a website as well. So TLS is something that we all use every single day, and I think it's pretty much the perfect example of a hybrid crypto system. And yeah, as mentioned, this next diagram is from Cloudflare, so shout out Cloudflare. Thank you for this useful diagram. So just to kind of walk through what's actually happening here when the TLS handshake happens, the first thing is that the client is going to contact the server, and the server will send the client a certificate and a public key. Once those have been sent over, the client will verify this with a trusted root certificate authority to make sure that they are who they say they are. Next, the client and the server will negotiate the strongest type of encryption that each of them can support. Once that has been established, the client will encrypt the secret key with the server's public key, and it will send it back to the server. Once the server has that key, the server will decrypt all of the client communication with its private key, and then the session is established so that asymmetric encryption process has now happened and the session is open. So then the session key can be used to encrypt and decrypt any data that's going back and forth between the client and the server from that point forward. Other examples of different things that, again, you probably have used before or may have used right before the session. A lot of mobile chat systems use this. If you're using Signal or WhatsApp, this is the way that they generally do it. Again, it's way more complicated than what I'm talking about here, but the general idea of how it works is using that system. Signal. Oh, I thought I had another thing after that, but maybe not. Another thing that's really important in part of this process is the key exchange. And so one of the most widely used is called Diffie-Hellman. And this is so that you can set up that agreement between the two parties so that they can begin exchanging the data and can do so over an insecure channel or a public network. If you are using elliptic curve cryptography, you can also use sort of a special type of Diffie-Hellman that's elliptic curve Diffie-Hellman. Again, so you can start sending secrets even if the channel isn't secure. Oh, this is what I was thinking I had. So Signal also has this triple Diffie-Hellman protocol that they've been using, and it's pretty interesting. They have a lot of stuff up on their site of how they've architected it and put it together. So if you're interested in this kind of thing, definitely check out what they've been doing there. Okay, let's dive into some key management. Key management, I find not to be the sexiest topic, but it is really important when you are doing anything related to encryption. Some of the sort of most important key points with key management is that obviously the keys need to be accessible to the data, but they need to be inaccessible everywhere else. And they need to be stored away from your data. So you need to make sure that they're available when you need to encrypt or decrypt the data. But when that's not happening, they are stored away somewhere securely where they can't be accessed and tampered with. As mentioned, the longer the key size, the stronger the encryption, generally. Is that true in a general way? Okay. Are there exceptions to that? Mm-hmm. Okay, cool. So it does differ between the type, the strength of the keys. So like it's not really it's more of an apples to oranges thing when you're comparing asymmetric and symmetric algorithms. So for example, like elliptic curve cryptography requires a key length of more than 512 bits in order for it to be as strong as a 256-bit AES key. So you can't really compare them one-to-one in that case. You want to make sure that you're generating only one key per purpose. So there may be a lot of other cryptographic operations that you're doing that aren't just encryption, again, like hashing or signing or things like that. But you never want to use the same key for more than one operation. You also want to make sure that they're randomly generated in a secure environment. We'll talk a little bit more about different types of secure environments in which you could use for key generation. This is a super basic example of how you could generate a key if you wanted to. There are a lot of libraries that you can use that will basically let you choose what algorithm you want to use and the length of the key that you want to use. So the generation process can be pretty simple, but again, it's where you're actually storing it and how you're getting it back out that's going to be really important. Another thing to consider is implementing secret sharing. So if you want to split up the secret or the key into multiple parts, you can do that to add another layer of protection. And then you can only use that key again once you have all of the parts of the secret reassembled. There are two main ways to do this. There's Blakely's scheme and Shamir's secret sharing. Both of them are fine to use, but Shamir's secret sharing is a bit more efficient, so that's the one that people generally tend to prefer. I also really wanted to know when I was like researching this, like if Blakely and Shamir had beef, if they were like competing, because you know how there's always stories of like mathematicians that were like competing with each other. So if anybody knows if there's any drama there, I would love to hear about it after the talk. Key storage. So you want to store your keys somewhere where they cannot be tampered with. Most people opt for using some sort of like vault storage for this. HashiCorp has a vault product that's quite good, and it's open source as well. So you can either use their managed service or you can do it on your own. The company I work for does that as well. And this just ensures that your keys are stored away, they're protected, no one can touch them, and they're only used when you actually do need to do some sort of encryption and decryption. You also want to have some type of plan for rotating the keys out. If you are not beholden by regulation and compliance, this can kind of be whenever you decide. The general ballpark rule is between 90 days to a year of changing out the keys. However, if you are beholden to PCI DSS, HIPAA compliance, any of those really long acronyms that have something to do with very sensitive personal data like healthcare or finance, then they do have particular rules about how often you have to change out the keys. They call this a crypto period, and really there's no set crypto period per se. It's really dependent on a lot of different factors that you're choosing, like the length of the keys, the strength of the the algorithm that you've chosen, and also the security life of the data in question. So you do want to make sure, and usually when you're going through that compliance process, you have to do a lot of work around this anyway, because they're going to be looking to see what your process is for this. So just make sure that you keep that in mind and agree with it with your team, or if you're working on your own, that you're clear on what your plan is for rotating out those keys. And also revoking the keys in the event that they are compromised. If a key is compromised, you need to immediately revoke it anywhere it's being used and rotate it out. So to that point, it's important to have a recovery plan because these things do happen. Of course, we don't want to think about it and we don't want to fear it, but it is important to have a recovery plan in place should your key become compromised. Because again, there's really no point in even doing encryption if the key gets compromised. So you need to think through who you first need to inform if this happens. And you need to have a method for rekeying, which would also involve knowing anywhere that that key has been in use, and anywhere that that key has been stored. You also want to monitor all of the rekeying operations to prevent it from being made vulnerable again. So next, we're going to talk about where to actually perform encryption. You actually have a lot of options today. There's a lot of choice as to where you might want to do this. Sort of the highest level that we can think about is encrypting within software or within your application versus encrypting on your hardware. So we'll start with hardware because there's fewer options with hardware. It's pretty much two that you have choices between. The first one is full disk encryption. So this is encrypting your entire machine, all of the file system info, all of the content, basically anything that's on that machine. And this is really great because no matter what happens to the device, if someone gets a hold of it, if they're not an authorized user, then they can't access it. And there's specific full disk encryption practices like pre-boot that you can opt in for so that you can't even boot up the operating system unless you're an authorized user. You can also encrypt any removable devices that you have because, again, if you've got this fully encrypted machine, but then your USB has a bunch of stuff on it that it shouldn't have, like keys or whatever, then it won't really matter that you have the machine that's encrypted. There's also now some features within some platforms. I know Canonical just released a trusted platform module option for encrypting your machine. So the trusted platform module is a separate part of your machine that is cryptographically protected. And anything that is put inside of the TPM can't be touched and it can't be tampered with. And it uses an attestation process to ensure that what you put in it is what you want it to put in it, and also that no one else can access it. So this is a really great part of the machine to actually do some of that key generation and key storage in. But again, it's not available on every machine. It's only within certain ones. There's also file level encryption. So if you want to be a bit more granular about your access control, then you can ensure that specific files and folders will remain encrypted. The benefit of using file level encryption is also that when files are copied through the network, they do stay encrypted. So there's a data at rest and a data in transit sort of aspect to this that provides an additional level of protection that you wouldn't get if you were just using the full disk encryption option. Okay, so now we'll talk about software. There's a couple of places where you can do encryption within your applications. The first is at the client level. So if you ever use sort of like a front-end library that has some sort of encryption option, this is happening at the client level. This will ensure that before it hits your infrastructure or goes over the network, all of the data will be encrypted. This is also sometimes called field level encryption. MongoDB has field level encryption that you can set up. And the benefit of this over, for instance, server-side encryption is that it's never your data is never going to hit infrastructure or anything in plain text. It'll stay encrypted no matter where it is in the process. Whereas if you're encrypting something on the server side, maybe in C++ or Python, or something like that, it is still going to hit your infrastructure in plain text at a certain point. Once that encryption process happens, then it's protected, but there is a little bit of time in there where it remains unencrypted and it could be exposed. Database and data storage level encryption has been around for a long, long time. You've probably used this before in some form. Some databases kind of just have it set by default. If you're using Amazon S3, they now have AES turned on for all of the buckets that you set up. You can turn it off if you want, I think, but it's not recommended to do that. So this is great because it just makes it easy, but sometimes easy is not always better because sometimes you just let it run and you don't really know what's happening. So use the database level and the storage level protections, but make sure that you pay attention to what's going on, what type of algorithm they're using. And also another thing to keep in mind is I just pulled this Supabase example because they did a good job of explaining how they have encryption available for the column level and encryption available for the row level. And you might think, oh, wow, great, let's just encrypt everything. Why not? But the thing is that is going to introduce latency. When you are encrypting things, it does make everything run a bit slower. Sometimes it's like on the order of milliseconds, but sometimes it's a lot longer than that. So if you're worried about latency, it is important to think about, is this data actually data that I need to encrypt? Is this actually sensitive? Is it required by regulation? So just think through that when you're trying to decide where exactly you want to encrypt the data. Another kind of cool advancement that has been really taking off over the last couple of years is the use of secure enclaves, which are also sometimes called trusted execution environments. So unlike a TPM, these are a separate part of your operating system, but it's not a separate part away from the operating system. It's a hardened environment within your own CPU that will work kind of in the same way, where that anything that happens inside of the secure enclave can't be tampered with, and it also uses attestation to ensure that that happens. So no matter what someone's privileges might be within the system, there's no way that they can access anything that's happening inside of this secure enclave. So this is also a really great place to do anything that you might need to protect. You can send data fully encrypted into the enclave, and it will only decrypt once it's inside the enclave. You can run whatever process you want and then send it back out fully encrypted. There are a number of different companies that make chips that do this. RISC-V is an open source option. The rest, as you can all see, are like big tech companies. NVIDIA actually just released GPUs that do this. So previously people were getting kind of excited about it, but then they were like, well, we can't do anything machine learning related. We can't do anything AI related. But with the TEs available from NVIDIA, there is a possibility now of doing that. There's also a bunch of different cloud providers that offer this. Sometimes it's also called confidential computing. Confidential computing is kind of like the big umbrella term for utilizing TEs and secure enclaves. So if you go to a cloud provider and you search for it, that's probably what they're going to be calling it. There's also loads of open source projects that let you do cool things with TEs. There's ones that allow you to just run things in a Docker container and deploy that inside of a TE. So you can use, whatever code you were running, and you don't have to be beholden to a very specific type of architecture that maybe like Amazon or Google are requiring for you to use it. And again, some of these are open source, so you can use them immediately. Some of them are more managed, and you have to pay for them. We'll take a quick look at a few encryption libraries and some resources if you are curious about getting started trying out encryption. I really liked this article, because when you start looking into encryption, everything says, don't roll your own, don't do encryption yourself. And it's a bit like cheeky, but this person is saying like you actually should roll your own cryptography. And the argument that they made is that you should do it so that you understand how it works, not so that you can actually use it in production. It is helpful, and I'm totally guilty of this at times of just finding a library that will do what I need it to do and not really digging down into what's actually happening and then being like so confused why it's not working the way I want it to. But if you are really curious about encryption or you think it's going to be really beneficial to your code and to your business, then it's worth it to give it a go and dive in and try to see how it works under the hood. So definitely try writing your own, but don't use it in production. Definitely don't do that. So a few libraries that are pretty vetted and that people have recommended. One is the PyCryptodome one for Python. That was the example that I used earlier for key generation. Crypto.js is one for JavaScript. There's a few Rust crates that are available. The one thing that you need to be careful with any library, obviously, is just making sure that it's tested and that it's vetted. So there's a few Rust ones out there where they say, I've built this, but it's not tested and it's not vetted. This one, Rust Crypto, has been tested and vetted, so it's fine. .NET has some built-in namespaces that you can use for that. And then obviously there's probably a lot of C++ developers here. So the Crypto++ library is good if you're writing C++. And it has a bunch of different cryptographic schemes available in there that you can try out. A couple of others that have come up and that people have spoken highly of. One is libencrypt. So it has a pretty easy to use API and they only offer symmetrical algorithms with this. So again, you are limited to just the single key algorithms there. Another one is Borzoi, which is the benefit of this one is that it's aligned with international standards, and there can be kind of some tricky things that happen when you're accounting for different standards when you're building things globally. But they do have the sort of most widely recognized and highly secure algorithms available there. And then the last one that has come up quite a bit is this one, which is a separate module from the new Privacy Guard. And it's open source, so you can try it out and use the APIs that they have there. So when you're using a library, just a couple of things to think about, which we've kind of already talked about a little bit. You want to pay attention to the algorithms that are available. A lot of the libraries that you might use are probably being updated, but it's important to just make sure that they actually are using the algorithms that we've all swiped right on and not the ones that we've swiped left on. You also need to make sure that they meet all of those regulatory requirements. For instance, one that I've seen come up a lot when it comes to PCI DSS is that they require that you use 112-bit key lengths and that you use industry-tested algorithms. So you want to make sure that you're not only using the proper key lengths, but also that the algorithms that you're choosing and using do meet those standards. So when time comes for you to be reviewed, you won't be burned and have to rebuild everything. You also want to be careful about making modifications to any of the libraries that you're using or any of the code because not only can it compromise the keys, but it can also change the data as it's being sent around. So beware of making any sort of modifications unless it's just for having a play and trying to see how it works, which is, of course, perfectly fine. So coming to the end here, just a couple of little things to wrap up. Some of the most common attacks that you might see when it comes to encryption. The first one are brute force attacks. So this is, just hammering it, trying to find something by trial and error that will work for compromising a key or a credential. There's side channel attacks, which have more to do with data leakage. So this is where you want to be really careful of where those keys are being used and where they're being stored. This really doesn't have anything to do with the algorithm that you choose. It's more about how you're handling the keys and the data. And then, of course, the man-in-the-middle attack. So this is where someone might try to intercept the public key and then change the public key as it's being sent. So just be aware that these are the types of things that you would be needing to protect against when it comes to encryption. There's also this term that's been used a lot. What's called zero trust security, which is really this idea that nothing within the system should be trusted. And the way that encryption sort of fits into this idea of zero trust security is that if you protect the data and no one can access the data, no one that's not trusted can access the data, they can only access it when it's in an encrypted form that they can't see, then you're golden. There's really nothing to worry about, because even if they were to get a hold of your whole system, they're not going to get any of the data, any of the sensitive information that you don't want them to have. Another thing to point out that isn't like necessarily related to encryption, but it is tertiarily related. This is a statistic from CrowdStrike, but more than 80% of attacks involve credentials. Credential leakage is really a big problem. And one of the ways that you can solve for this is by encrypting any of the credentials that you have, only decrypting them when you actually need to use them for some type of sign-on or authorization. So that's something to think about. Another thing to consider is using these different tools that exist to sniff for secrets to make sure you're not accidentally exposing your credentials somewhere. I've definitely done the thing where I accidentally pushed a secret to GitHub, and then it immediately told me that I did it, which is great. So again, not necessarily directly encryption related, but when we're thinking about building that fortress around everything that we're trying to keep secure, there are a lot of different methods that we can employ, and they all work together to make sure that we're keeping that data safe. So the last two things we'll talk about are fully homomorphic encryption and post-quantum cryptography. So when we're thinking about encryption, these are sort of like the two things on the horizon that everybody's keeping their eyes on. Fully homomorphic encryption would allow data to be used essentially without ever being decrypted. So the data in use problem is sort of being solved right now through the use of secure enclaves and trusted execution environments, but there probably will be a day in which we just use fully homomorphic encryption, and then everything is protected. We're still likely a ways away from this being a reality, but there are researchers working on it now. The next thing that everybody's talking about is post-quantum cryptography. So once we have these quantum computers, they're going to solve all of the encryption algorithms and break them, and then we're all going to be screwed. Not really, but that's the fear. And there's also this fear that there would be a possibility of harvesting the encrypted data that currently exists and then using those quantum computers to decrypt all of that data. Oh yeah. Just asymmetric algorithms, sorry. So not all algorithms, just asymmetric algorithms would be the ones that the quantum computers would be able to break. So there's a couple of sort of practices or things happening right now to get ahead of this. The NIST group has created, I think, 4 post-quantum algorithms that they're working on. Signal has now upgraded their specification to this post-quantum extended Diffie-Hellman. And then recently, Google also added support for quantum-resistant encryption in Chrome, and I think in one other product that I can't remember the name of right now. So to wrap things up, the secrecy of your message should always depend on the secrecy of your key, not the secrecy of the encryption system. So again, just kind of hammering home that point that it really is so important to keep the keys safe and secure, and make sure that you've got a plan in place should they be compromised. So just some things to think about if you are wanting to start employing encryption into the applications that you're building. Think about what data actually should be encrypted, again, because it can get expensive, it can increase latency. So really, what is that most sensitive data, that personally identifiable information that you want to protect? Where will encryption actually happen? What scheme will you decide that you want to use? And then also, where are you storing the keys and how are you going about storing the keys? So in this talk, we covered some different encryption algorithms and schemes that you could choose to use, some practices around key management and some things to think about for protecting your keys, different libraries that are available that you can try out. And then also just thinking toward the future of, worst case scenarios of what could happen, hopefully won't happen to you, but also things that are coming down the line that we should be aware of. So in the end, just don't throw away the key, but also don't store it with your data and make sure that you rotate it regularly. So thank you all so much for coming to this talk. I hope that you were able to get something out of it. There's a couple of minutes left, so if anybody has questions, you can either say them now or you can just find me after and we can have a chat. But yeah, thank you guys so much for coming.